So we are going to discuss about interpolation. And interpolation is in two versions. There's what we call interpolation of equally spaced tabular points. And we also have interpolation for unequally spaced tabular points. So we'll start by discussing methods which are applicable on the interpolation of values which are equally spaced. So interpolation is the process of computing the value of a function y equals to f of x for any given value of independent variable x when some values of the function y equals to f of x for certain values of x is given. So for example, you may be asked, find f of 20 if f of 19 is given by 5, f of 21 is given by 10, f of 23 is given by 14, f of 25 is given by 31, and say f of 27 is given by, say, 46. Or find f of 3 given f of 0 is 6, f of 1 is 10, f of 2 is 20, f of 4 is, say, 36, f of 5 is, say, 49. Or we can have the problem find f of 46 given f of 36 is 40, f of 38 is 37, f of 40 is, say, 31, f of 42 is, say, 29. So cases whereby you are finding the value of the function for an x value outside the range given is called extrapolation. While when the x value is between the range of values of x given, we simply say interpolation. But let it be noted that interpolation of values either within or outside the range will not have a difference in terms of the formulas that you are going to apply, whether we are going to be approximating the values of the function for x, either within the interval given or outside the interval given. So what matters is to understand different types of the interpolation formulas and know how to apply them, because those methods will be used to do both approximation of values of the function within the x value interval given or outside the x interval values given. So, methods of interpolation. So there are two things to consider. There are methods based on equally spaced mesh points, and there are methods which involve unequally spaced mesh points. So for A, we have Newton forward interpolation formula. Which will be abbreviated by NFIF, or some people say Newton forward difference formula. So then that will be abbreviated by NFDF. So the word interpolation can be replaced by difference. And then number two, there's Newton backward interpolation formula. Abbreviated by NBIF. Then there's what we call Newton divided difference formula. And then number four, there's what we call Lagrange interpolation formula. Number five, there's what we call Gauss forward interpolation formula. Number 6, this goes backward interpolation formula. Number 7, there's what we call Bessel's formula. Then there's what we call Starling's interpolation formula. etc. So those are some of the different interpolation formulas you will use to carry out interpolation of equally spaced mesh points. So there's just another one here called Avery's interpolation formula. So for the case of unequally spaced mesh points, we make use of these these formulas here. So the Lagrange interpolation formula and Newton's divided difference formula are the ones we use to carry out interpolation in case the spacing between mesh points is not necessarily uniform. So these two methods, 3 and 4, applies for both equally spaced mesh points and unequally spaced mesh points. So we will not discuss all these different methods that we have listed 1 to 9, but we'll majorly concentrate on the Newton forward interpolation formula, Newton backward interpolation formula, Lagrange interpolation formula, but that does not mean that the rest of the formulas will not be tested. So that's just for the purpose of class discussion. So you'll get time and see what happens in those other different types of formulas. Once we discuss those main 3 interpolation formulas, you will be in a position to read and understand how the other types of interpolation formulas work. So the first one, Newton forward interpolation, or we say difference formula. So we can use the word interpolation or we can use the word difference. Both of them mean the same in this context. So consider n plus 1 equally spaced mesh points. So we have x naught, x1, x2, x3, all the way up to xn. Then let y equals to f of x be the function which takes on the values f of x naught, f of x1, f of x2, f of x3, all the way up to f of xn. And remember from our previous discussion, we said f of x naught can be written as f naught, f of x1 can be written as f1, f of x2 can be written as f2, f of x3 can be written as f3, all the way up to fn. So then now, we know that since xi's are equally spaced, then any general value of x is given by x xp equals to x naught plus or equally spaced mesh points. How do you get a general xp value with reference to the x naught? From our earlier discussion, if x naught plus pH, correct, x naught plus pH. So this is a result that we actually obtained from our previous class, that for equally spaced mesh points, all other mesh points can be obtained from the first mesh point, x naught. So a general x or xp is given by x naught plus pH. So, which means that the function f of x can be written as f of xp, which is the same as f of x naught plus pH. And then this is nothing but shift raised power p of f of x naught. I.e., we are saying that f of x is equals to shift raised power p of f naught. Do you understand how we are obtaining the relationship between f of x and the shift raised power p? Are you able to see how I'm obtaining this this relationship? Good. So this is how we're obtaining it. So if you go back to the definition of the shift operator, we said that, so this is just by the way, the shift of f of x. Remember that shift of f of x is given by, from the definition. F of x plus h. Correct. F of x plus h. So it's like the shift of f of x takes you to the next f value, which is x plus h. Then the second shift of f of x is the same as f of x plus 2h. Okay? And we saw that if you keep on applying the shift operator, we get this. So that's why f of x naught plus ph is written as e raised to power p times f of x naught. And then x naught, f of x naught can just be written as f naught. Okay? So then with that in mind, also recall that how can we write the shift operator in terms of the forward operator? Shift is the same as in terms of the forward operator. Correct. 1 plus the forward operator. These are results that we already shown from the previous class. So then that tells us that we can rewrite this as f of x is equals to 1 plus forward operator raised to power p of f naught. Then from your calculus class, you recall this. That if I have 1 plus x power n is the same thing as 1 plus nx plus n into n minus 1 over 2 factorial x squared plus n into n minus 1 n minus 2 over 3 factorial x power 3 plus other several terms. Which theorem is this? Provided that absolute value of x is less than 1. So which theorem is this? Correct. So this is by binomial theorem. So we will make use of that binomial theorem on this part. So we make use of binomial theorem on the right-hand side of this equation. And so we say using binomial theorem, on 1 plus forward power p, we have f of x will be given by one plus p forward plus p into p minus 1 over 2 factorial second forward plus p into p minus 1 p minus 2 over 3 factorial third forward plus other several terms. And then I have f naught outside. So this is nothing but f of x is equals to, so I'm multiplying everything by f naught in this bracket. So I have 1 times f naught is f naught plus p forward of f naught plus p into p minus 1 over 2 factorial second forward of f naught plus p into p minus 1 p minus 2 over 3 factorial third forward of f naught plus all other several terms of the same kind. So this formula is what we call the Newton forward difference or interpolation formula. So this is what we call the Newton forward interpolation formula. So this is the Newton forward interpolation formula or Newton forward difference formula. So let's call it 1. In mathematics, you must always understand when and how to apply a formula. Knowing the formula is not enough. You need to understand when and how to apply the formula. So NB to apply Formula 1, we choose X naught so that the absolute value of P should be less than 1, i.e., P is a number between -1 and so absolute value of P should be less than 1. And to have a small error in the computation, and P should be between 0 and 1 to have a small magnitude. of triangulation error. Another thing to note, that one applies when we are approximating the value of f of x near the beginning or top of the difference table. So for me to test whether you understand how to interpret these conditions, I will not go directly into the example first. I'll derive the second formula, the Newton backward difference or interpolation formula. And then we'll do a problem combining both the two formulas. And then from the example, then we'll be able what is the distinction when it comes to applying the two formulas. And then another obvious thing is that for you to apply one, then the spacing between consecutive xi values must always be uniform. So this Newton forward interpolation formula only works for equally spaced mesh points. If the spacing is not uniform, then you can't apply it. So let's derive the next one, Newton backward interpolation formula. So we begin in a similar manner. Let x naught, x1, x2, up to xn be equally spaced mesh points. And f of x naught, f of x1, f of x2, all the way up to f of xn be the corresponding values of the function y equals to f of x. We can add the term respectively just to keep the order. So because we have already said that the mesh points are equally spaced, so we know that for any general x value, we have x, which can be written as xp, is x naught plus ph. What makes us to have that relation is because we have said these mesh points are equally spaced. So therefore now, this implies we can write the function f of x as f of x naught plus ph. And then we can express f of x naught plus ph in terms of the shift operator, which will be e raised power p of f of x naught, which you can just write e raised power p of f naught. So because our discussion is with respect to the backward difference, we will express the shift operator in terms of the backward. So how do you express the shift in terms of backward? From last class discussion, shift is the same as? Come again? Correct. So it's the same as 1 minus backward raised power negative 1. Eh? So I hope your formula is the same as this. Yeah. So which means then we'll have f of x is nothing but e raised power p f naught, but where this e we replace by 1 minus backward raised power negative 1. Everything here is raised power p times f naught. And then from loss of indices, a power n is a power mn. So which means f of x will be the same as 1 minus backward raised power minus p times f naught. So we make use of the same binomial theorem on this right hand side coefficient of f naught. Just as a reminder, I want you to change the role of n to minus n and tell me how will we write 1 plus 1? You can't see the screen? Okay, some can, some can. Okay. How will we write the binomial expansion of this? 1 minus x raised power negative n. First term will be 1, correct? Second term, nx, correct? And then next term, minus m, and then so negative x squared. So then we can simplify. So you see there's a negative outside n, and we can also factor negative outside minus n minus 1. So in simple terms, the coefficient of x squared will be so you see here I can have negative 1 and then we have negative 1, then n, or if you can split this to see clearly how everything is becoming be positive, we have this negative n times, when I factor out negative 1 here, I'll have negative 1 into n plus 1. So then this negative and this negative 1 cancels out. So I just have n into n plus 1, and then over 2 factorial. When I square negative x, I get positive x squared. So then the third term of this expansion will be nothing but n into n plus 1 divided by 2 factorial times x squared. N into n plus 1 over 2 factorial x squared. What will be the next term? Yes. They let's check and see whether they will be negative or they'll still be positive. So we are just changing the role of, so where there's n, we put negative n, okay? So we'll have negative n into negative n minus 1, negative n minus 2. We are going to have over 3 factorial into minus x power 3. This is what we'll have, okay? Yeah, let's see. I hope everyone agrees that the the product of these first two terms will give us what we have in the previous term. It will be n into n plus 1. Are you able to see that? Yeah. And then when you raise a negative number to an odd power, you get a negative number, okay? Yeah. So we'll have a negative x power 3 here. And then this remaining term, we can factor out negative 1, and we'll have n plus 2. So do you see that all the negatives will cancel out? Yeah. So the term will be n into n plus 1, n plus 2, divided by 3 factorial x power 3, etc. So the structure will be the same. The next term will be n into n plus 1 times n plus 2 times n plus 3 over 4 factorial x power 4, etc. So applying that to this equation, we'll have f of x equals to 1 plus p backward plus p into p plus 1 over 2 factorial backward squared plus p into p plus 1, p plus 2 divided by 3 factorial backward power 3 plus other several terms. Then I multiply by f naught. So this is by binomial theorem. Because of binomial theorem. We do the same process that we did previously. So multiply each term by f naught. So I'll have f of x will be f naught plus p backward of f naught plus p into p plus 1 over 2 factorial backward squared f naught plus p into p plus 1 p plus 2 over 3 factorial backward cubed f naught, then plus other several terms which take the same structure. And this formula is what we call the Newton backward difference formula or Newton backward interpolation formula. So this is the Newton backward interpolation formula, or we call it Newton backward difference formula. So we call this one 2. In a similar way as in our first formula, we need to know when to apply the Newton backward interpolation formula and how. So note, to apply formula 2, we choose absolute value of p to be less than 1 and to have a minimal translation error. And then we pick x naught to be a value at the bottom of the difference table. It is my assumption that the exercise I gave you did it on how to draw difference tables. So loosely speaking, the Newton backward interpolation formula is only applicable when you want to do an approximation or interpolation of a function for a value of x that is near the end or the bottom of the difference table, while the Newton forward interpolation formula is most suitable when you want to carry out interpolation of f of x for a value of x that is near the beginning or the top of the difference table. So let's demonstrate how we can apply the two different formulas to solve an actual problem. So example, consider the table below for function so we have x, we have f of x, so -1, f is 0, 0, f is -1, 1, hello daktari. Mzuri sana. Niko Chiromo. Yes, yes. And prefab the class just a few minutes, then maybe I can come. Yes, yes. Najuanga hiyo SOMAS, sijui SOMAS. Yes, yes. Sorry for that small technical problem. So 1, f is 0. And then 2, f is 15. So find an interpolating formula not we are interpolating an interpolating polynomial, not really formula. Interpolating polynomial that fits all the points using 1 Newton forward interpolation formula and 2 Newton backward interpolation formula. Can you be trusted in drawing the difference table for this table? Okay, it's not yet your turn to suffer, it will come. So solution. First, we draw the difference table. So we have x value, we have f value. So x begins from -1. You skip a line, then 0, skip another line, 1, then skip another line, then we have 2. Then when x is -1, f is 0. When x is 0, f is -1. When x is 1, f is 0. When x is 2, f is 15. So this will be the first forward difference of f, second forward of f, third forward of f, etc. So what value will I put in this space? What number? For those who are stupid enough to do my assignment or exercise, what number should I put here? -1, correct. So the difference there is -1. And then what number will I put in the next step? 1. Which number should I put here? 15, correct. Remember, if you did my work, the way we get the differences is usually the lower number minus upper number. So here they are getting -1 by saying -1 minus 0 is -1. 0 minus -1 is +1. 15 minus 0 is 15. Good. Then the next difference in the second column, next column, 2, 1 minus -1 is 2. Next, 14. Good. And lastly, 12. Good. Good. So in general cases, the first number here is what we call x naught. This will be x1, this will be x2, this will be x3. Then this is f naught, this is f1, this is f2, this is f3. Then this will be the forward of f naught, forward of f1, this is forward of f2. Then this is second forward of f naught, this is second forward of f1. And this is the third forward of f naught. Please, if you didn't do the exercise I gave, I urge you to go and do it, because all the problems we are going to solve on this interpolation will be requiring you to do a difference table and interpret it to ensure that you know that. So for the Newton forward interpolation formula, this is what you are going to take. And then there's this diagonal. If you check from what you have drawn, these numbers, which has f naughts, are along that given diagonal, whereby the x naught is specified as -1, f naught is given by 0. So we know that a general x value is given by x naught plus pH. So the question is, what is h in this given problem? What is the space between two consecutive x values? What is the mesh spacing in this problem? 1. spacing, we just take the positive quantity. So the difference between 2 minus 1 is 1, 1 minus 0 is 1, 0 minus 1 is 1. So h is 1. So then, which means, and then x naught is given by minus 1. Replacing them in this formula, we'll have x equals to minus 1 plus p times 1, which is minus 1 plus p. So what's the value of p? What will be the value of p in terms of x? X plus 1. X plus 1. So p is equals to x plus 1. So you write your formula that f of x by the Newton forward interpolation formula is given by p by f naught plus p forward of f naught plus p into p minus 1 over 2 factorial second derivative of f naught, second forward of f naught plus p into p minus 1, p minus 2 over 3 factorial third derivative of f naught. Now I'm stopping here because if you check our difference table, we can only define up to the third difference. That's why I'm stopping here. But if the table was big enough up to fourth and fifth differences, then you extend the formula. So the value of f naught in this problem is 0. So I'll have f of x equals to 0 plus, where there's p, you replace by x plus 1. And if you check the difference table, what is the numerical value of forward of f naught? -1. This is the value. This value, -1. So replaced by -1 plus p is x plus 1. Then p minus 1 will be just x. 2 factorial is 2. And then what is the value of the second forward of f? 1. Really? You can see, you should be able to see the diagonal here. So these are just the values. You read this value along the diagonal. So this is the value we are referring to. So 2. So 2 plus p is x plus 1. P minus 1 is x. P minus 2 is x minus 1. 3 factorial is 6. What is the third forward of f naught? 12. So I put 12 here. So I want you to simplify this right-hand side of f of x and tell me what kind of function are you getting? Open brackets and simplify. Tell me what is the nature of polynomial we obtain after simplification. So open the brackets and then collect like terms, then tell me. For what polynomial are you getting? The coefficient of x cubed is 2, correct? 2x cubed, and then next term plus x squared minus 2x minus 1, correct? So if you have a different answer from this one, it's an answer but a wrong one. So it should be, this is the correct answer when you simplify the right-hand side of f of x. So that is the solution to part 1. So part 2 is to get the same function, but now using Newton backward interpolation formula. So step 1 is to draw difference table. So let's redraw the difference table for the case of Newton backward. So I have x, f of x. I have first backward, second backward, third backward. So x are starting from -1. You skip a line 0, skip a line 1, skip a line 2. Then when x is -1, f is 0. When x is 0, f is -1. When x is 1, f is 0. And then x2, f is 15. So which number should I fill between -1 and 0? -1. 0 and -1. Remember, the way we get the differences when you have numerical values is the same. Take the lower number, subtract the upper number. So lower minus upper. So 0 minus -1 is +1. Then next difference, 15. Then the difference between 1 and -1. 2. 15 and 1. 14. 14 and 2. 12. Remember, the table is exactly the same as for the backward difference, for the forward difference table. What will make the difference is only the labels, but in terms of the numerical values, they will not change. They will be the same numbers. So when we derive the Newton backward interpolation formula, we say that for us to apply the formula, we begin, or we take our x naught to be the value near the bottom of the difference table. So that's what you are going to do. That -1, 0, 1, and 2, the value that is at the bottom of this difference table is 2. So then now you will pick this, and then together with this diagonal. So let it be noted that the way we read the backward of f naught, second backward of f naught, fourth backward of F naught, third backward of F naught, etc. When we want to interpret the Newton backward interpolation formula, they are actually not exactly the same values if you are to interpret the table in general form. What matters on how to pick the backward of F naught, second backward of F naught, etc., is where you are going to fix your X naught. And Newton backward, your X naught should be a number that is near the beginning of the difference table. So that's why we fixed 2 and then 15. And once you have your X naught and F naught, then you pick that diagonal. So this number is what we'll call the backward of F naught, second backward of F naught, and then third backward of F naught. Please do not confuse this with the way you drew the general backward difference table and how you are labeling the differences. I don't know if I'm clear on that. For those who did the exercise, you should be able to understand what I'm trying to say. The way we interpret the backward of F naught, second backward of F naught, etc. When you're doing a general table, we will not read it. I will not read the values the way I'm labeling in this diagonal. But these labels in the diagonal is with respect on what we need to substitute correctly into the formula for Newton backward. Am I making sense? Good. So, okay, assuming I was not on a Newton backward interpolation formula, what number will define backward of F naught? If I was not in the formula, but I was to interpret the value of backward of F naught, it will be which number? And then what will be the, so remember in most general case, your X naught should be -1 and F naught will be 0. If you are not fixing the values into the interpolation formula, if that table was given to you to interpret in general case, the first number is what will fix as X naught, the next corresponding value of F is what will be your F naught. But in terms of the interpretation of the Newton backward interpolation formula, we read our F naughts from the bottom diagonal, okay? So with that X naught value, we write the formula X is given by X naught plus PH. So what is X naught? In this case is 2, F naught is 15, and what is the value of H? H is 1. So X equals to 2 plus P times 1, so which is the same as 2 plus P. So what does P get? X minus 2, correct? Yeah, X minus 2. So then now you write your Newton backward interpolation formula. So Newton backward interpolation formula is given by F of X equals to F naught plus P backward of F naught plus P into P plus 1 over 2 factorial second backward of F naught plus P into P plus 1 P plus 2 over 3 factorial times third backward of F naught. I'll stop there because my difference table does not allow me to read values beyond third differences. If it was allowing that, then I can extend the formula. So we substitute accordingly. F of x, f naught is given as 15. P is x minus 2. So what is the backward of f naught? 15, correct? Then plus x minus 2. So x minus 2 plus 1 is x minus 1. 2 factorial is 2. Then the second backward of f naught, 14. And then plus x minus 2. So x minus 2 plus 1 is x minus 1. X minus 2 plus 2 is x. 3 factorial is 6. Then the third backward of f naught, 12, correct. I have 12 here. So I want you to simplify and tell me the polynomial that will be obtained for this second case. Anangojea ingine afanye. So what are we getting? 2x cubed plus x squared, x cubed product. Yeah, so it's exactly the same thing as what you obtained in previous method. What is already expected, because we are dealing with the same function, then you don't expect to get different answers, even if you use different methods to get this to get the answer. So sometimes once you have gotten the polynomial of the function that interpolates the values, you may be asked to use your function of the polynomial to approximate some values. So for example, if you're asked to find f of 0.5, what will be the value? Now that you have the function. Also find for me the value of f prime at 0.5. Find for me f at 1.5. And then find f prime at 1. Also f second derivative at 1. So if you get any of the answers, you say. So simply means that if you're asked to find f of 0.5, where there's x in your function, you put 0.5 and put the values in your calculator and get the numerical value. Negative? Everyone to confirm that is correct. Is that correct? Someone has negative 2. Any other different answer? That this may be the only question you can answer in the cut of the exam. So in order to get it. Apart, so -5/4, -2. So which is which? Is there anyone else with a different answer from these two? For f at 0.5. -1.5. So I did and I got -1.5. So yeah, so -3/2. So that's what I got. But probably for those who are getting -5/4 and -2, recheck. I don't mean that my answer is the perfect one, but because someone else has also gotten what I gotten, what I obtained, then probably the teacher is always right. So it must be -3/2. Then f prime at 0.5 means you will differentiate the function and then replace 0.5. Confirm, everyone to confirm whether the 0.25. Any other different answer? So there's another 0.5. 0.5. So probably maybe those ones, I don't know the answer. Confirm. And then f at 1.5. I will advise you to revise your Form 3 notes on how to use a calculator. That is 5. I also had 5. Yeah. F prime at 1. Oh, 6. Okay. And then second derivative at 1. 6 and 14. Or 14 is for the last part. Okay, good. Fine. So that is how we apply the, to make things clearer, let me re-explain this. That sometimes when you are given a table of values of X and a table with corresponding values of, say I have, say, 0, then 0 0.2, 0 0.4, 0. Assume this is an arbitrary function whose X values are given as what I have in this table. And then assume that this is 5, 7, 10, 14, 19, 30, 38, and then 58. But I assume that we have an arbitrary function, f of x, such that when you put in the values of x, then these are the corresponding values of f. So we are not doing the whole problem, but I want us to 0, 0.2, 0.4, 0.6, 0.7, 0.8, 1.0, 1.2. Please make this table. It may be useful to you when you want to interpret some of these problems. So I have here as 5, this is 7, this is 10, 14, 19, 30, 38, and 58. I have this table. We want to use it to interpret some things that probably when you start solving problems on interpolation, you will need to know before you start solving. Assume I want to approximate the value of the function at 0.1, or I want to approximate the value of the function at 1.3, or I want to approximate the value of the function at 1.5, or I want to approximate the value of the function at 1.1, or I want to approximate the value of the function at 0.3, or I want to approximate the value of the function at 0.9. I'll say 0.7. I want someone to tell me what will be the most suitable formula for me to apply if I have to do the approximations for this given f values, and why you think the formula is what you want to say. F at 0.1, what would be the best method to apply? Is it Newton forward or Newton backward, and why? Newton forward, reason? Correct. So if this was the table and you want to approximate f at 0.1, then the correct formula to apply will be Newton forward interpolation formula. Reason, 0.1 is near the beginning or the top of the difference table. So that is what we will use to get the correct approximation. And in that case, what will be taken to be x naught? So remember the 0 point, you identify it in the difference table. So this is where you'll have 0.1. So it's a value near the top of the difference table. So the correct formula or the best formula to apply to eliminate a lot of errors in the computation will be the Newton forward. So what will be the x naught? 0, correct. X naught will be taken to be 0. Then if at 1.3, so 1.3 you identify it in the difference table, so this will be where we have 1.3. What best formula will be used to approximate that? Newton backward reason. Is 1.3 at the top? At the bottom, yes. And what will be a correct x naught? 14. 1.4, not 14. 1.4, correct. Then 1.5. Newton forward or Newton backward? Newton backward because it's still at the bottom. Newton backward interpolation formula. What will be the x naught? Yes, now remember now, 1.5 will be outside this one. And so remember, for us to pick x naught, it must be among the values of given in the question. So the closest x naught in that context would say be 1.4. Then 1.1. Newton backward, x naught. So note that 1.1 is a number between 1.0 and 1.2. So what would be the correct x naught? 1.2. So because when you use Newton backward, then it should be near the bottom. So the number 1.1 is sandwiched between 1 and 1.2. So we pick x naught to be 1.2. If at 0.3, Newton forward, x naught, 0.2. Then 0.7, if you are to measure these numbers, you will say this is the top, this is the bottom. And then what do we say about area around 0.7? Middle, correct. So this middle. So let it be noted that for Newton backward interpolation formula, to get a better approximation of the value of the function, you must be very, very close to the bottom of the difference table. And for the Newton forward interpolation formula to give a better result, you must be very, very near the top of the difference table. But when you are in between or at the middle of the difference table, then neither of these two formulas are going to give better approximations of the result. So to do or to get better approximations when you want to pick a value of x that is near the middle of the difference table, you apply what we call Bessel's formulas. Then we have the Stirling's interpolation formula and Everett's. interpolation formulas. So go and check and make some notes on how the formulas for Starling, Bessel, and Ibris looks like, and how to apply them. So write the formulas and give at least 1 or 2 examples in each case. And they are most applicable when you want to do the interpolation near the middle of difference table. So the take home is that we have discussed 2 main interpolation formulas, Newton forward and Newton backward. Both formulas are applicable when some conditions are satisfied to give better approximation. 1, to apply Newton forward, you must be dealing with values that are near the beginning of the difference table or at the top of the difference table, while to get a better approximation for Newton backward, you need to be near the bottom of difference table. If you have to do any approximation or interpolation of values near the middle of difference table, then Newton forward or Newton backward are not the best. They'll give larger magnitude of errors. So the correct formulas to apply will be Bessel, Starling, or Ibris. And then sometimes from the problem itself, you will be able to find the actual interpolating polynomial or function. But in some cases, the interpolating polynomial is not necessarily important. For example, in this case, when you want to interpret the value of f at 0.1, in this given example, you will use this so we'll have general x is given by x naught plus ph. So for in this context, what is the value of h? What is h in this given arbitrary example? 0.2. And then what is x naught? We want to approximate f at 0.1. 0. So then now this value you want to approximate is what we call x. So you'll substitute into this formula, x you put 0.1, x naught you put 0, h is 0.2, then times p. So then now this will give you 0.2p equals to 0.1, which will mean p is a half, correct? So p is a half. So therefore, when you write your Newton forward interpolation formula, you replace everywhere this p by a half, and then replace with the respective forward differences from the formula and get the numerical value of f at 0.1 directly. So the interpolating polynomial will not be useful in that case. If you are specific at finding the value of the function at a specified value of x, so you'll not get the actual f of x. You'll just get the exact value of f of 0.1. Okay? So I wish to stop at that point, work on that exercise. Next time we meet, we'll be discussing about interpolation of f of x when x values are unequally spaced. Have a good day. Question, yes? How does the middle begin? That is, I'll answer by a question. You know how to find median, eh? If you are given some data points, eh? Yeah, so you can always partition your number line in terms of what is at the top or what is to the left, to the right, and at the center. So that's the measure. So when you have identified the median, then you can see the distance between the median and the other endpoints. Then you should be able to know the top and bottom and center. I don't know if that one is answering your question. I get it. Get an example to say that. Okay, okay, good. Okay, have a good day.